guys, so what we're going to do is we're going to start off, well, where we left off. And so hopefully you saved that file that we were last working on about the etchant. So open that up. Yeah, I can send it in the email. I'll do that right now. Okay, so let's see, we're going to go open. And we're going to click on our chemical etch file, chem etch 1. And it's .mph is a file type. And so we left off, I think we left off just after geometry, because this is the total geometry here that we wanted. And that's good. So, and so while you guys are loading that up, let me go to the board and remind you guys what we're doing here. Okay, so we have this etchant coming in, and the etchant type is copper chloride. And so this copper's coming in. So we have these two boundaries right here, and we're going to define these two boundaries as our copper chloride. And this is like the bulk constant value at those stages. This right here is going to be our outflow. And this right here is going to be our inflow. This surface right here is actually open, but we're going to assume that the flow of our etchant is coming in this direction. And at this level right here, at this boundary, that's just a constant level of this etchant material. And so we're going to put a condition here. It's going to be no slip. Okay. However, it's going to be at a constant velocity. And I believe we're going to do like 1 millimeter per second. And that's, so at this boundary right here, the etchant is moving along at this concentration, at this bulk concentration. We can even call this bulk here. Same here. At that bulk concentration at 1 millimeter per second, okay? And it's coming in right here. It's inflowing right here. So this is going to be, you're going to have some pressure here at the outflow, but you're going to have this non-slip boundary condition. And so what's going to happen is that right here, right next to the wall, you're going to have that velocity, which is going to be 1 millimeter per second. But as you move away from the wall, it gets a little less and less, right? And right here, it's going to be 0, moving along right there. But that's like, you know, what the profile looks like going this way. But it gets a little strange in this area because you have a dip in here. And also, this is going to start being etched away. Okay? And because the flow is in this direction, and it's coming down here and out there like that, you're going to have more material. The etch rate over here is going to be higher than the etch rate over here. So it's going to start, you know, looking like this. So this area right here is going to etch a little faster just because that's the direction of the etchant coming in here. And over here, you're not going to have as much movement, right? Because, you know, you're having this etchant come in here. You're etching away material from the surface. And so in order to have the same concentration of etchant etching away at a certain rate, you want to get that material out of there. So the area is freed up to have more concentration of the etchant coming in. And so that's why you're going to have more etch rate over here than over there. Yeah. And this is going to be a moving boundary. So this boundary is starting right here, but it's going to start moving out in this direction. And so it's going to have a certain velocity of that surface. And it's going to be our surface. It's going to be, moving at a certain velocity. And so it's a moving mesh, so it's not remeshing every time, but it's morphing what the mesh elements look like over time, which is kind of interesting. Okay, so that's where we're at. Okay, so let's go to so let's label our moving boundary. So this boundary right here, we're going to need it later, so we're going to name it now. So this boundary right here, just at the bottom, the part that moves, we're going to label all of these boundary elements. We're going to call it one thing. So how to do that, we did this before on another example, but we're going to do it again. So what you do is you right click on definitions, you go to selections, and then you click on explicit. Okay, and then we're going to name this up here. See, right here is called explicit 1, here's called explicit 1. We change the name here, it's going to change the name over here too. But later on we can pull out a menu and just pick our boundaries we selected. So let's call this moving boundary. Okay, and now we're going to not select a domain. So remember, these are domains right here. We don't want to select a domain. We actually want to select a boundary. Like these edges are the boundaries. We could select points too. Whatever you guys want to do in the future. But we're going to select boundaries. And the boundary that we're going to select are just a part that's going to move. And it's going to be this piece, here, here, and here. So it's all 5 of these. And so those are labeled 4, 6, 13, 15, and 16. And this is the only boundary in the entire simulation that's going to move. Okay. So next we have to tell it what the material is in here, and it's going to be a liquid. So let's go to material properties. Let's right click on it and say add material from library. And then what we do, we come over here, and then let's go choose some liquid like water, just some liquid. So go here, go down until we come down here to liquid water. Click that, highlight that, and then we click on add to component. Once we click on that, it should add it over here, and there we go. Now we don't need to change anything over here. It's just letting it know that all these boundaries right here, it's all water. Okay? Now let's go to transport diluted species, and then so in here where's our I'm looking for a convection right here. I'm sorry, it's in here. Transport properties. That's why I was looking in transport diluted species, but let's look in transport properties. Look for concentrate convection, which is right here. We will call it, we'll say the velocity field, and velocity field. Then down here, we'll type in this D, which is our diffusion coefficient. Okay. And then let's go to concentration. So right click on transport diluted properties, and then click on concentration. And then for concentration, we are going to select a couple of boundaries. So right here and here. So remember what I told you over here, we're just going to call this some bulk copper chloride right here. That's the concentration at those boundaries right there. But remember, everything above here, even out here, is all copper chloride everywhere. And then at this boundary is like the last constant value of that. And then within here, it's changing its concentration because it's etching this stuff. Okay, so check this box right here. And so for our concentrated species, we're going to call this, if you remember, it was C, capital CU, capital CL2 underscore bulk. And that's what we're naming these two boundaries, 1 and 3. Okay, that's letting you know what the moles per meter cube is for that. Now for outflow, let's click on this and say outflow. We have to let it know that it's this boundary right here. So click on that boundary. And for the flex, let's click on, right click here, type in flex. And then for our boundary selection, put in our moving boundary. This is what we labeled last time, so we created this. And it's going to automatically select this boundary that we named before. Remember these these 5 boundaries? It'll put that in there for us. And then for inward flex right here, we're going to choose our species, and we're going to put here our surface. And that's what we have down here. Okay, so we're done with the transportation of diluted species. Let's go to the deformed geometry now. Let's right-click that and do the free deformation. And let's select domain 2 only. So this domain is the only part that is going to deform during our simulation. These other 2 domains are going to stay constant, but this one will deform. Now let's right-click on it again and look for 0 normal mesh displacement. So 0 normal mesh displacement. Here's 0 normal mesh velocity, but we want the displacement. So click on that, and then click on these 2 boundaries right here, this one and this one. So these boundaries right here only get longer, okay? They just get longer, but they don't go, they don't displace in the vertical direction. Now let's right-click on this again and do the look for prescribed normal mesh velocity. which is right here, prescribed normal mesh velocity. And then we go to our moving boundary, the one that we created. This is the only part that moves outward in this direction. And then we're going to type in the velocity of that, the meters per second. That's going to be our v underscore surface. Okay. Now let's go to our laminar flow, the next part down. Right click on that and click on wall, and that should be wall 2 here. And for wall 2, just select this boundary number 3 here. And then for that one, remember, we're going to say this is no slip, and that's the velocity right there. So it's number 3 here. It's already no slip, so we can just leave it there. And let's click on wall of movement. What we'll say is manual. So we're going to key it in ourselves. And it only has an X direction. It doesn't move in Y. So we're going to put in 1 and then square bracket millimeter per second. So mm per s. So that means that it's just moving along this horizontal like that at 1 millimeter per second. Now let's do our pressures right here, the stress pressures at the ends. So let's go right click and put in boundary stress, and we just have to click on this boundary right here, the inlet and the outlet. Okay, so we're done with that. Now let's go to our study. And for this, we actually want to do time dependent. So right click on study, go to study steps, go to time dependent, and then click on time dependent. Okay, you guys got that? So yeah, so it was study, and then go to study steps. That opens up to this. Go down to time dependent, and then go over here and click on time dependent. And for this, here's the default range. We want to change this. We're going to have it go for 10,000 seconds. But it's going to go faster than that. Sometimes, it's not the norm, but sometimes your simulation actually goes faster than the actual time that you're putting in. This is one of those cases. So that's 1 with 4 zeros. And the step here is 500 seconds. And I mean, so these are the steps it's going to show us at those steps. Okay. And now we just click on compute right above and see what it gets us. Yes, it's about a third of the way done right now, so not going to take too long. Almost there. I some kind of singularity issue. Hey, do you guys have the same error that I got?
Yes, sir.
Huh. I think I missed something here. Let me backtrack a little bit. Okay, let me just go through what I just told you guys. So we got the moving boundary.
Yep. Be a collector.
Oh, okay, so I did miss something right here. So when you guys, okay, so click on deform geometry, okay? And I forgot to do the order right here. So, so this is it's like a polynomial, and you want it to be first order polynomial, not second order. And also, the mesh smoothing type, you want that to be hyperelastic. Hyperelastic is like very large deformations. Maybe some of you have seen it like this, where it happens a lot when you guys want to simulate rubber. So for example, this is like stress strain curve right here. This is like normal elastic. So that's elastic if it follows this trajectory. Hyperelastic may go something like this. You know, it has some really strange behaviors. Like for example, if you have some rubber ring, right, and you want to deflect it, a little bit, it'll just spring back up. But if you want to deflect it a lot, let me make a thinner one. If you want to deflect it a lot, it'll like flare out like this and go in like that. And that is a totally different kind of deflection, and that's where you want to use like hyperelastic if you're doing some very large deflections. Okay, so I'm hoping that's the only thing. Let's find out. So let's go back over to time dependent, and then compute. See what happens. Okay. Hopefully you guys got something. It should look something like this. So did everybody get this? No? Are you still running it?
No, mine is, I don't have like that laminar flow area in the top. Mine's like that big circle thing. It's like up in the middle of the red area.
Wow.
It's probably the boundary.
Yeah, it does sound like a boundary condition. Oh,
Yeah, right?
look at that. Oh, did you do like a no slip? That's my guess is like when you go to I think wall number 2 right here. I think it might be this where you have to put in no slip for the wall condition, and down here you put 1 millimeter per second. Is that? Do you have that?
Got that? Yeah.
Wow. Okay. Um, I'm not sure about that one. Okay, so so one thing I want to show you guys. Every time you do like a parameter sweep or you do a time trying to dependent type of thing, you can click on animation and click on the player, right? Then it'll go through and it'll save all the images like this, and then you can go over here and click on repeat and just click play, and then you can play this back over and over again to see get a better understanding what's going on. And let me try to zoom into this a little bit. Zoom extents. Yeah, so what you're looking at, what's being plotted on the surface here, and this is also right here, this is the concentration. So the concentration right here of the copper chloride is really high, on the edge is really high, okay? But as it comes in here, the concentration is really low because you're etching away species on the surface here, but this is the only part that's exposed. This right here is not copper. This down here is copper. So you're using copper chloride to etch into the copper material. And it has some other material that is unaffected by the etchant. So that's why this is not moving at all. Another thing you could look at is this right here is the velocity profile right here of the fluid. And this right here, this is the pressure field. So like each line right here is a certain type of pressure. Okay, and so you can see how that is playing out throughout this. If you go back to this right here, and again, any 2D geometry, you can click on it, and then I'll show you the value of that concentration of what you're trying to show here. From here, let me lift this up a little bit. So it has a position, X and Y, and it'll show you the value of whatever is being plotted. So if you're interested in a certain location, you can plot out some data. You can get this data right here and also plot it out if you like by making manual clicks to that. Okay, so I'll go ahead and save this and put it online for you guys. Also, if you want to save yours too, you can. So the next thing I want to do is to look at diffraction patterns. So we talked about this a little before, but basically so we're going to model something like the two slit experiment. So we'll model something like this. It'll be a semicircle. We'll have two wave sources coming in, light sources coming in this direction, going through a slit here and I guess in real life you would think of it like this. You're having something here, a slit. The distance between these is d right here. And then it's going to go onto some wall. And so what happens is that this incident wave coming in, and when I'm drawing these lines of a wave coming in, so basically everywhere I draw a line, that's a peak, and in the middle is like a minimum, that's a maximum. So think of it like this, like if this was a wave, it would look something like that. And this is a peak of that wave coming in. So some incident light coming in here, it goes through these two slits here, and if you remember back from physics, if your slit is on the order, the size of your slit is on the order of the wavelength of that light, it sort of acts like a pinpoint that just emanates in a spherical fashion like this. And again, each of these lines right here correspond to a peak of that wave. So you have a wave going off in this direction, a wave going off in this direction, and in this direction right here. Right? And the same thing here. Here's another. You could think of this as an independent light source that's just there shining, right? The nice thing about it is that they're both in phase, right? But it's an independent light source, and it's emitting a spherical light pattern. And where these things overlap, right here, you're going to get constructive and destructive interference when these things overlap. And so, far away, you're able to see the pattern of these things interfering. Now, when they, for the interference pattern, you're going to have a max at sine theta. I think that was, what was that? N lambda over d. Lambda is the wavelength of that light. Okay, so the wavelength, like from one peak to another, is lambda. D is the slit right here. N is the order of the interference. So you can start from 0, then you have like the next peak. So the next peak is 1. Second peak is the next one after that is n equals 2, and so on. And I think the minimum is like you're multiplying it by n plus 1/2. I think, but anyways, the nice thing about that is people can use that to do spectroscopy. So here's like an example. I have a picture here. Let me show you guys. See this right here. Okay, so down here is frequency. Oh, the difference, like the relationship between frequency and lambda. What is that? That's so frequency and lambda is equal to the velocity. In this case, is light, so the velocity is c, 300 million meters per second. So here's the relationship. So if you know, we know c, right? And if you know your frequency, then you can find your lambda. Or if you know your lambda and c, then you can find the frequency. Okay, so, so if you're shining, so every type of molecule has its own fingerprint, its own type of spectra that it gives out. And what I mean by spectra, for those of you who are unfamiliar with that, it's like if you're looking at, this is like frequency right here. You could do spectra of musical instruments. You could do spectra of any kind of material. But basically, every molecule is going to absorb and emit, certain frequencies of light, and they're going to have different levels of intensity. And so you can plot that out, right? And so, I don't know, I'm just drawing some random thing right here. That could be the fingerprint of some type of virus. or some type of molecule that's in food. It could be anything. This is how they look at stars that are very far away and determine what the stars are made of, right? So what you're looking at here is something that looks like it has several different types of things. Like right here is, I wonder if I could get a pin here. Like right here, here, like this is all the same kind of, it looks like that's from the same species, but as these are the peaks of that particular molecule, right? And so, yeah, it's all mixed together with several different things. But the thing is you know, molecules have very unique fingerprints, and so you can use that to identify things. It's a whole lot easier when you have a pure type of compound, but instead of a mixture, right? And also, there was a video I want to show you guys too of this. Yeah, so this is like going through two slits. So it comes out, and you can see how they, this right here has this interference kind of pattern going through that. Yeah, I was wondering what happened to this Schrodinger's cat. Okay, so, yeah, these patterns even happen even when you have very large apertures, where still every single piece is a source of light, like a pinpoint of light that's emitting. And if you just have a very large one, you just have many more pinpoints of light that you're starting out at. And if you have a lot of them, it just looks like one wave going through, but it's really multiple sources if you want to think about it like that. But anyway, so let's model that. Okay, so let's go back up to CompSol, and that's saved. So let's go to New. And this time, when we go to New, we're gonna make our own differential equation, our own partial differential equation. Okay, so we're not really going to use a model. And so this is like an introduction where it's showing you guys how to put in your own equations. So let's go, it's going to be 2D. Okay, but this time let's go to mathematics, and we're going to go to PDE interfaces, partial differential equation interfaces, and click on coefficient form PDE, this one right here. Now this is a pretty general PDE, but we're going to make some of its coefficients 0 because we don't want all the coefficients there. We're trying to create the Helmholtz equation. Now I'll show you guys what that is in a second. So add that, and then go to Study, and then Stationary, and then you're done. Okay? And so let's make the geometry first. No, let's do the parameters first. We'll do the geometry, then I'll tell you about the equation that we're going to use. So go to parameters, and let's key this stuff in. It's not that many parameters. So lambda, 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 that's going to be 0.1 meters. So use units of meters. And K, that's going to be our wave number. Okay? So the wave number is related to lambda. And the wave number is going to be 2 times pi. In this case, pi is in radians, right? So we're just going to tell it, it's in radians, per lambda. Okay, so this is k right here, wave number. That's the wavelength. U0, lowercase u0, so this is going to be the incident wave, and so this is just going to be the amplitude. So let's just call it 1, the amplitude of the incident wave. Now we're going to solve u. That's the amplitude throughout the entire space. So you have this 2D space right here, right? And then you have these waves coming in. So remember, you have these waves coming in. Of course, we have it in a tube. That's not really a big deal. So these waves are coming this direction, right? Then they emit out like this. Then we will see their interference pattern. But the u that we're solving for is all in this space. It's like u as a function of x and y, all in this space right here. So that's what we're solving for. That's our unknown in our equation that we're solving for. And let's also put in some geometry for our, some parameters for our geometry. Let's put L1. That's going to be the length of those guys right here. So 0.5. Let's put in W1. That's going to be the width. And let's put in 0.03. There's also going to be an offset because they're separated by D here. So offset, let's put in 0.1 as an offset. Okay, yeah, so that's all that. Now let's go to geometry. It's already 2D. So let's put in, first let's do our circle. It's not going to be a complete circle. That would be 360. So this is 180. So let's change our sector angle to 180 instead of 360 degrees. And also let's slightly shift our position. So let's put, let's see what this looks like. Build that. So it looks like that. So we got to rotate it a little bit. Let's do a rotation of -90. Build that. Okay. And then for this X position, let's make this L1. Go over to L1 and build that. Okay. So there we go. Now let's do a rectangle. We'll make one rectangle, then we'll copy it. Okay? So our first rectangle, the width is going to be L1. The height's going to be width, W1. Right? And so if we just build that, it ends up right there. But that's at the center, so we want to we want to position it a little lower in the Y position. So go down to the Y here, and then put negative W1 divided by 2 minus offset. And so that just shifts it down a little bit. Okay. I could have chose better parameters. I should have said like D over 2 or something like that. And if I would have did it over again, I would have put a parameter here called D and made that be the distance between there. But this is a poor choice, I admit. Okay, so go to geometry and put copy. That's going to be in a transforms. Go down to copy. And then for the copy field for displacement, Oh, choose the one you want, because there's nothing in there right now, so choose the rectangle. That'll be R1. And for the displacement field, you're going to put, let's see what our parameters are. Yeah, put 2 times offset. Yeah, 2 times offset. Yeah. Okay. And now let's do a union. We want to get rid of those boundaries between those. So go to geometry, go to Boolean, and union. Control A, click on there, go Control A, unclick the keep interior boundaries, and then build all. Now we just have 1 structure now instead of 3. And that's it for the geometry. It's a very simple one. Okay, so now we're going to go deal with that PDE. And so go to our coefficient form, our PDE, and look at the equation. See that equation? This is what we're dealing with. And if you look underneath here, even open up these other things at the bottom here. Okay, see all these coefficients, you have that EA, DA, you have the C, the alpha, gamma, you have beta. Let me move this over here. You have A and you have F. Those are all these things right here. And you can pick and choose which ones are 0. And the ones that are not 0, you can tell it what to put there. And so the equation that we want is the Helmholtz equation. And I'll write that down for you over here. So this Helmholtz equation looks like this. Got it into. And remember, U right here, this is the amplitude, this is the field, you know, U of xy, we're solving that in there. Minus, right here, k times u equals 0. So this is what we're solving here. Remember what k is right here, the wave number? We're solving this equation for u. This right here, a lot of people may have seen it like this, depending on your background, the Laplacian. Okay, this right here is a differential operator. Now that's one equation. The other equation is for the influx and outflux. So we're going to take these as an influx, and this surface right here is going to be the outflux of that. Otherwise, it would just, you know, reflect back in. We would have a different interference pattern if we did that. But for that, we're going to have and we will key this in, but I'm just showing you what the equations are, and you'll see how we're going to key it in. So this is for the inflow. Here's the outflow. Okay, again, the outflow surface right here, and the inflow surfaces are right there. Okay, so we have to make that equation right here look like the Helmholtz equation. Okay? So that means changing a couple of things around and canceling out a few other things. So the ends are normal vectors. Yeah, yeah. Exactly. Yeah, that's exactly right. So, see this absorption coefficient? So for that right there, we're going to make it be this right here. So this absorption coefficient A is right next to U. We want that to be negative K squared for the Helmholtz equation. So let's change that. So negative K hat 2. Okay? So for C, we want that 1. It's already 1. That's good. So if that C becomes 1, then we have that first part for the Laplacian. For F, that's 0 in our equation, right there. So make that 0. The E0, 0. The dA, we don't have this term right here. So our amplitude is not changing as a function of time. It's stationary. So we can make this 0. We could leave it 1 because it's stationary. It's not even going to count it anyway. But also the alphas are 0, the betas, that's 0, and the gammas, those are all 0. Okay? So again, we're using some very general PDE equation, and we're forcing it to be some physical equation that that models the behavior of light interference patterns. Okay. Now, once we're done with that, let's go to right-click on coefficient, and then let's choose our flux source right here. Flux or source. Click on that. And now we're going to define our inlet and our outlet. So for our inlet, let's choose this boundary right here and this one. You might have to zoom in to get that. Okay, on mine it's 1 and 4. And then down here, this is our equation we have to put in. Is from this piece right here, our inflow. So that's going to be negative I times K times U. That's the first one. Plus, the second term is 2 times U0 times I times K times, then you have that exponential part, so exp for exponent, exponential, and then it's negative I times K times X. Okay, so again, that's this equation right here that we're keying in, right there. Now let's go. Oh, this right there? Yeah, I got, let me see if I can make that bigger. I know what I could probably do. Yeah, this is what I want you guys to key in right there. So you got this term and that second term right there. Okay, cool. All right, now let's do the same thing with actually with the other one, we could just copy and paste this. So copy that negative I times k times u. Just copy that and paste it in our next thing. So let's go to coefficient and do another flux source. So this is going to be our outflow. And so we're going to highlight this boundary and this boundary. And then here, just paste that negative I times k times u. Okay. Okay, so that's all there. Now let's mesh it. Now, if you remember, we didn't really mesh our last thing. We just jumped past mesh. And if you do that and go straight to compute, it's going to just do the normal mesh, and that's fine. But sometimes you want to really define your mesh because you have to be very careful in certain things, in certain situations. In this case, when you're modeling wavelengths, light, electromagnetic radiation, those kinds of things, you want your mesh, and they say this in ComSci as a rule of thumb, you want your mesh size to be a fifth of the wavelength. Okay? They say that, that or smaller to get a good result. So, yeah, so go to mesh, right click on it and do free rectangular. Then go to size, and then click on custom. We're going to make our own size. And then for the maximum element size right here, because see the algorithm in the mesh, it tries to generate mesh automatically, and in the small areas it'll be a really small mesh. In the wide areas, it'll tend to grow. And so you want to make a limit on the maximum size that it grows. And you want that size to be a fifth of your wavelength. So we're going to put lambda divided by 5 right there. And then if you do build all, you'll see what I'm talking about. See that? It looks pretty dense here. But if you zoom in here, you can see that the maximum size, so if it's like a fifth, we're talking like 1, 2, 3, 4, 5. So like maybe from here to here is a, I don't know, wavelength, something like that, I don't know. But and also out here, if we didn't do that, the size of the mesh elements out here would be quite large. But we had limited the maximum size to be lambda over 5. So that's why these over here look just as big as, just as small as these in here. Okay. So then go to study, and then press compute. And so it should look something like this. Now you can see here, actually let's change this pattern right here. So if you go to, you open up 2D plot group and you click on surface, it gives you an option of changing how your color scheme is set up. Right now it's set up as rainbow. Let's set it up as wave light. Okay? So we change the wave light, it looks like that. And you can clearly see here that the red here, these are the peaks. 0 here is where things are at 0. And these are the maxima in the negative direction. And so if you zoom in here, You see, like from this peak to that peak, that's like one wavelength, and that should be like about, I don't know, 5 of the mesh element sizes. You can see here where the interference is, right? And again, you can click on any of these points right here, and it'll tell you what that amplitude is at the bottom here. Let me try to move this up. Yeah, it gives you the value of that point wherever you click. So if you're here, you click right there. It's going to be that value. Click right here. So the blue is going to be negative, red is going to be positive, and this white part right here should be the null value right there, so it'll be close to 0. Yeah, 0.046. Yeah. Okay, so that's that example. And you guys could do other things. You guys could play around with this. And in fact, for an assignment, I'm going to think of something that you guys can do with this. Like maybe choose like some other types of geometries. Maybe put an obstacle in here. See how the light, goes around the obstacle and still has an interference pattern. Just try something interesting, But so I'll come up with an example. I mean, an assignment that you guys could do before we meet again next Tuesday. Okay. So any other questions about this example? Okay, great. See you guys next Tuesday.